Day 134, Honors Physics, Electrostatics, Capacitors, homework example number 39. Once again, you're going to be simplifying this capacitor network. There's no battery yet, but they're going to tell you in part B to hook up a battery to points A and B. Once again, you have to identify the parallel and series portions of this. So let me go through that. If I'm at point A and I want to get to point B, I have two pathways, two what we call branches. We'll define that more officially next week. But I can go from A to here, and then go up and over to B, and back to a battery that we got attached. Or I can go over and down and around to point B. You can't back up. So there's two branches. Those two branches are in parallel. But in this top branch, there's two in a row. Those are in series. The 2 and the 4 microfarad capacitors are in series. We're going to put those together first. And to put those together, you use the rule that 1 over C total equals 1 over 2 microfarads plus 1 over 4 microfarads. Do the calculation. Comes out as 1.33 microfarads. I'm going to go to 3 sig figs just to kind of keep this a little bit more accurate. Don't go to 4 sig figs though. If it were a lab, you certainly wouldn't want to even go to 3 sig figs. But we're doing a homework problem. I'm going to let you go to 3 sig figs. The bottom line is you're going to need to draw a new diagram. The new diagram will look like this. Basically, we're replacing those two capacitors at the top with one capacitor, and then the bottom one stays the same. Point B is still over here. It's going to hook up a battery in a minute. So the top capacitor is now 1.33 microfarads, and the bottom one's still the 6 microfarads. So these two are in parallel now, and it's an easy rule in parallel. They're on two different branches, two different pathways from A to B. You just simply add them. So you get the quick answer here if you're just trying to find the equivalent capacitance of the total network from A to B. 6 plus 1 is 7.33 microfarads. So that's the answer to part A, actually. So we got part A done. But part B now, so you hook up a battery. So what I will do here is I will come and hook up a battery. It doesn't really matter. I'll do it the other way this time. Short one there, long one there. It doesn't really matter which way you hook up the battery at this point. The negative side here, positive side there. We don't really care about that. But the battery is going to charge the capacitor. It's going to move some electrons around, charge the capacitor. And we're going to say that the battery is hooked up to points A and B, so it's maintaining a potential difference, a voltage of 30 volts. And I'm a little out of space, but that's 30 volts. The battery is 30 volts. That's all I got to worry about is batteries, is their voltage. But capacitors have 3 values. There's C, Q, and V. So down here, you start with this bottom diagram always. You're going to use C equals Q over delta V. Delta V is 30. C is 7.33 microfarads. Micro equals Q over 30. So what does that come out to be? 22? Or 220. Q comes out to be 220, I believe, 220 microcoulombs. If you multiply 30 times 7 is 210, plus 30 times 0.33 is another 10, 220 microcoulombs. That's the charge on this capacitor, 220 microcoulombs. All right, so here's what you have to do. You show that work, especially show that work. So I want to see your diagrams like this in steps, this initial work here, this work here. Now some of the other steps I'm going to allow you to slide on. For example, what I really want you to do is just start writing the numbers down. You can start when you do these enough, you'll start just looking at them and putting down the numbers in the appropriate spots. For example, in this middle diagram now, the 1.3 microfarads and the 6 microfarads, you got to ask yourselves, what do they have in common? Do they have the same charge or the same potential difference? Well, the rule is they're in parallel, they have the same potential difference, and that is 30 volts. They're the same as its replacement down here at the bottom. They're both 30 volt potential difference. So once we know their potential difference, we know 2 of their 3 values. Once again, every capacitor has 3 things, C, Q, and V. So now we're going to do, for each one of those separately, we're going to plug into C equals Q over V for each of those 2 capacitors. Now I'm going to do that off to the side and tell you what Q is going to be for each of those. I'm just going to write them down on the diagram. So I'm going to pause. Actually, I just noticed I don't even have to go to your calculator, because bottom one, for example, I'm going to be plugging in 6 for C, 6 micros, and 30 for V. So I'm going to have 6 here and 30 there. 6 times 30 is 180 microcoulombs. So I know I'm going to have 180 microcoulombs, that's 180 microcoulombs of charge stored in that capacitor. And likewise, this one at the top, I'm going to be plugging in the 1.33 microfarads as this capacitance, 30 volts here. So I'm going to have a 30 here times a 1.33 micro gives me 40 microcoulombs. You can double check the math there, but that's going to be 40 microcoulombs. And I know I'm on the right track because if I take that 40 microcoulombs charge plus the 180, 40 plus 180 gives me 220, which is indeed what the total charge stored on its replacement value is. So that's a check that works out. 40 plus 180 gives me the 220. They have to add up to the capacitance of, or the charge stored on this capacitor. All right, I'm going to keep working backwards. Bottom line is, this capacitor is done. What I mean done is that it has its three values. I've got the 180 microcoulombs of storage, 30 volts. I know its value. I know the three values for that capacitor. I'm done with that one. But what I don't know is these two up here in the top branch. But what do they have in common? Voltage, that's a potential difference, or charge stored. Well, in series, the rule is they have the same charge stored. What charge do they have stored? Well, it's the replacement value, the 40. So I know that each one of those has 40 microcoulombs of charge stored. 40 microcoulombs. They each have that stored. And I know their capacitance. So what I'm going to do now is, once again, I'm going to go to this equation. And I know for those two upper ones, let's take the 2 microfarad capacitor. I know I got a 2 microfarads here for that capacitor. And it's got a 40 right here, 40 microcoulombs. So if I plug in a 2 here and a 40 there, it's going to end up with a 20 volt potential difference, I believe, if you plug that in and work it all out. So you're going to get a 20 volts potential difference for that capacitor. And the one on the right, if you plug in the values, you plug in 4 here for its capacitance, 4 microfarads, and the charge of 40, it turns out to be a 10 volt potential difference. It's interesting that the larger capacitor, even though it could store more, it's not storing more here, it's storing the same amount. It has a lower potential difference. Okay, we'll come back to that, but you can think about that for a little bit. But the main thing here, though, to notice is that these two numbers add up to 30. That's your check. In series, their voltages add up. Their charge stored is the same. In parallel, they have the same voltage, but their charge storeds add up. Think about that. So that's what you're going to get used to in practice. All right, but the problem says calculate the charge and potential difference across the 4 microfarad capacitor. Oh, we did that. So we have the answer. Here's our answer, and we could also, I'll circle it in red. That's our answer to part B. I've got a 10 volt potential difference and a 40 microcoulomb charge stored on that capacitor. I could figure out also the energy stored by just plugging into that equation. I'll write it down. The energy stored in the capacitor is 1/2 CV. You could do that now as a plug and chug. That would come out in joules. So there's another good example.